Hello, today we will go over a linear time solution for longest common substring through suffix array and longest common prefix array linear time construction. A data structure for substring problems. Given a text T of length m and O m preprocessing time, the next input is a string S of length n whose occurrence or lack thereof in T should be deduced in O n time, or linear in terms of the second input. In other words, the initial preprocessing time is proportional to the length of text T, but thereafter a search for string S is done in time proportional to the length of S independent of the length of T. A suffix tree is a compact tree of all string suffixes that is constructed in linear time proportional to the length of the string. It utilizes repetitions as its organizing and resource-conserving method. Same characters share paths until divergence. If we can construct this data structure in linear time, we can answer many problems, such as longest common substring in linear time. A suffix tree as suffix array. A suffix tree can alternatively be described, represented, and reconstructed in linear time from a suffix array and an auxiliary data structure, a longest common prefix array. A suffix array for string S is a lexicographically sorted list of S suffix starting positions. So for banana, we would have indices 0 through 6 for banana, anana, nana, anna, na, and a termination symbol. When we sort these suffixes, it would be $, a, anna, anana, banana, na, nana for lexicographically sorted, and we would retain only the indices in our suffix array. A generalized suffix tree of two string inputs. For strings S and T, a generalized suffix tree would be of the form S pound T $, where pound and $sign are non-same termination symbols that do not occur elsewhere. A depth-first traversal and examination of the symbols at each leaf node indicate whether internal nodes belong to S, to T, or to both. Longest common substring is answerable by finding the deepest internal node containing both leaves in string length and number of suffixes on plus s time. You may have noticed the termination symbols at the end of each suffix and at each tree leaf node. Assume that the last character of S appears nowhere else in S. In that way, no suffix of the resulting string can be a prefix of any other suffix. To achieve this in practice, we append a non-alphabet character, such as $, to the end of string S, $. Inverse suffix array. Many suffix array construction algorithms utilize the inverse suffix array, in which ISA I equals J when SAJ equals I, asserting that suffix I has rank J in lexicographical order. SA and ISA are computable from one another in ON time, as ISA is also a permutation of 1 to n. Suffix array linear time construction. Kay and Sanders' 2003 skew algorithm is the first linear time direct suffix array construction. Suffixes are divided according to their positions. We firstly recursively solve a problem 2/3 the size of the original input by retaining only suffixes of indices I mod 3 does not equal 0, or 1, 2 mod 3. This suffix array 1, 2 of 1, 2 mod 3 suffixes in desired partial order is constructed in T 2/3 suffixes plus O suffixes time. For each position in the remaining 0 mod 3 set, pairs of indices I and I plus 1 is single pass radix sorted in OS time. Once the criteria of 2/3 of suffixes being sorted is met, The last comparison-based merging is almost trivial. Relative lexicographical order can be determined within 3 character comparisons, as I+1 entries can be stably sorted with respect to I entries with a pre-computed inverse suffix array. To illustrate, for suffixes at indices I and j with I mod 3 equals 0 and j mod 3 equals 1, the suffixes at I plus 1 and j plus 1 would have their relative order known as I plus 1 mod 3 equals 1 and j plus 1 mod 3 equals 2, and these are both in the 1, 2 mod 3 set. In general, any periodic set of positions according to a difference cover is a suitable alternative. Longest common prefix array. The longest common prefix is the lowest or deepest common ancestor of 2 nodes. The longest common substring has the longest common prefix between 2 suffixes of different termination symbols. The longest common prefix array contains the lengths of the suffix array's adjacent suffixes. We only need consecutive values as the suffixes are in lexicographical order. Let LCP ij denote suffixes si and sj's longest common prefix length. Then, within the LCP array, LCP I equals LCP SAI and SAI plus 1 for 0 is less than equal to I is less than j is less than n. So for a suffix array for banana, we have $, a, anna, anana, banana, na, and nana. For the longest common prefix array, we would calculate the longest common prefix between $, and a, which is none. Then we would calculate the longest common prefix between a and anna, which is a. Then we would calculate between anna and anana, which is anna. Then we would calculate the longest common prefix between anana and banana, which is none. And then between banana and na is none. And then lastly, between na and nana, they share na as their longest common prefix. So it would be 0, 1, 3, 0, 0, 2. The longest common prefix array linear time construction. Longest common prefix minimum range queries can be answered in O1 constant time after ON time processing. We exploit the balanced distribution as no suffix is involved in over 2 LCP queries at the top level of the extended skew algorithm for suffix array and longest common prefix linear implementation. Let Si and Sj be suffixes whose LCP ij is computed to find longest common prefix of Si minus 1 and Sj minus 1. Si minus 1 and Sj minus 1 are lexicographically adjacent suffixes. Si minus 1 equals Sj minus 1. Thus, a suffix can only be involved in LCP queries with its 2 lexicographically nearest neighbors of the same preceding character. LCP array from LCP 1-2 array. The LCP 1-2 array corresponds to the suffix array of 1-2 mod 3 suffixes, which contains the I mod 3 does not equal 0 suffixes in their desired order. So the LCP array can be computed from the LCP 1-2 array in linear time. Let j equals SAI and k equals SAI plus 1. Assume j mod 3 equals 1 and k mod 3 equals 2. Let j prime equal j minus 1 divided by 3 and k prime equal n plus k minus 2 divided by 3. Be corresponding positions in S12. Since j and k are adjacent in SA, j prime and k prime are adjacent in SA12. Thus, L equals LCP 1-2 j prime k prime equals LCP 1-2 inverse suffix array 1-2 j prime minus 1. LCP I equals LCP jk equals 3L plus LCP j plus 3L k plus 3L, where the last term is at most 2 and can be computed in constant time by character comparisons. Next, assume j mod 3 equals 0 and k mod 3 equals 1. If Sj does not equal Sk, LCPi equals 0. Else, LCPi equals 1 plus LCPj plus 1 k plus 1. Compute LCPj plus 1 k plus 1 as above, 3L plus LCPj plus 1 plus 3L, k plus 1 plus 3L, where L equals LCP1, 2, j prime, k prime, and j prime equals j plus 1 minus 1 divided by 3, and k prime equals n plus k plus 1 minus 2 divided by 3. Unlike in the first case, j plus 1 and k plus 1 may not be adjacent in SA, and j prime and k prime may not be adjacent in SA1, 2. Thus, we have to compute L through range minimum query in LCP1, 2, which is still constant time. This is how we solve LCP1, 2 range minimum queries in ON. The LCP12 array is divided into log n sized blocks, and for each block, A, B inclusive, we pre-compute and store. For all I in A, B, a log n bit vector Qi that identifies all j in AI such that LCP12j is less than minimum k in j plus 1 I LCP12k. For all I in AB, the minimum values over the ranges AI and IB. The minimum for all ranges that end just before or begin just after AB and contain exactly a power of 2 full blocks. If a range IJ is completely inside a block, its minimum can be found with the help of Qj in constant time. Otherwise, Ij can be covered with at most 4 of the ranges whose minimum is stored, and its minimum is the smallest of those minima. So we have gone over suffix array and longest common prefix array construction in linear time. And this answers our longest common substring problem in linear time.